think about that. That might be a fun little thing to put on the exam. So we're going to talk about chemical kinetics for the rest of the class. All right. So every lecture here, we're going to devote to this topic. And I love the reason why I devote so much time to this because I love kinetics and bias. And the reason why I love it is because it brings everything that we've learned back in. Kinetics requires us to understand thermodynamics and chemical equilibrium. We'll see that chemical equilibrium, we've already had some sense of this. Chemical equilibrium has something to do with kinetics directly. So we'll learn that. I'm not going to go too deep into kinetics. We're going to give you a taste of it. Kinetics can be a very, very simple topic. If we look at kinetics in the way that you may be doing Gen Chem, where you're thinking about how rates change with concentrations and things like that, that's actually not too hard. What I want to understand in the class for the first week or so, our first push is to understand the underlying principles of that type of kinetics. The idea of you have some rate of formation of products and it's proportional to some concentrations of the reactants. I want to understand the basis of that argument that you learned in Gen Chem. But we'll spend some time on that kind of kinetics where you're just looking at concentrations and the problems that's all about. In the second half of the module, we'll transition and looking more microscopically, where instead of thinking about concentrations and observable numbers like rates of concentration formation, we'll think about how molecules react. What's the physical process of a reaction, which will, as we'll see, involves collisions. And I want to understand the basis of collisions and what happens at the microscopic level. Our kinetics determined based on microscopic behavior. Right? We've seen time and time again that if we understand how two things combine and we take that idea and expand it to a mole, we get thermodynamics. And so if we can understand how reactions occur at the microscopic level, an idea, and then take that to the molar limit, you can understand kinetics that way as well. So we're going to look at kinetics from two different perspectives, a macroscopic and a microscopic. And we'll finish up with the microscopic, which actually can be quite complex. Oh, we're forgetting something here.
Yeah, I'm sorry.
What are we looking for? Oh, okay, very good.
Sorry.
No, that's okay. Don't worry about it. So I'm going to start with macroscopic kinetics today. The idea that we're just looking at changes in concentration. We're going into the lab and doing the kinetics experiment. And the kind of fancy scientific term that we talk about this kind of kinetics, we have macroscopic kinetics. There's a special term that we use for this, what we call let me spell that right. This is kind of a fancy word. Phenomenological rates in kinetics. So phenomenological is an interesting word. It actually comes from philosophy. And it's the idea that we're interpreting observable phenomena. So we're coming up with a kinetic model for our system by just observations, by using empirical data. Right? Using empirical. So this is like an empirical kinetic theory. Right. And we're just going to use the inputs, right? We're just going to think about the inputs that we give it in an experiment, right? So a function of basic, it's over here, experimental parameters right? And what are those? Well, temperature and concentrations. Right? Those are really the only two things that we have to control of reactants, rather. Right? Those are really the only two things we have to control in an experiment. How much stuff we put in and how hot it is. And what do we get out? Well, we get some products out. And the output of this process is the time derivative, the rate at which the products grows, right? The output is the rate of the growth of products. All right, so for instance, the example of just a very, very simple generic example of this is that we have some reaction A plus B goes to P, the product, an experiment, we could say that the derivative of the concentration of P with respect to time, right? How much, what we call the velocity, right? How fast the products form is equal to the concentrations of the starting material times some proportionality constant, which we call K sub R, which is the rate constant. There's some proportionality constant that takes input concentrations and temperature and gives you a speed of formation, right? That's kinetics. And these are all things that we can measure. You guys probably remember in Gen Chem, I'm sure you had a problem where you get a bunch of different concentrations for different starting materials, and you look at how the rate of product formation changes as you double or triple or halve concentrations, and you get some determination of the rates that way. And so there's a conversion factor that converts concentrations into that rate, the rate constant. Right, and I should really say, oh, of course, someone calls me right now, is that these of course have stoichiometric coefficients. So it might be 1 mole of A or 2 moles of A, and we of course raise the power of the concentrations to those stoichiometric coefficients. So if the reaction requires 2 moles of A, then our rate is proportional to the concentration of A squared. Right, this is phenomenological rates. Right, these are rates that we can determine just from looking at concentrations and looking at the concentration rate changes. It's all experimental data. The problem is this rate constant, right? This is the thing that we really care about. Right? That ultimately determines the kinetics. Right? And in phenomenological, doing this in an experiment, you can get KR. That's what you calculate in those problems. Gen Chem and so on. But KR is just a number, right? It's just a number. It's just some speed, some proportionality, but it doesn't really have any physical interpretation, right? It's just a number. Some reactions are fast, some are slow. And the question, of course, is why. So the thing we're going to focus on today in particular is this. We don't worry about what we call the rate law, right? This is what we call a rate law. We're not going to worry about the rate law, right? We'll come back to rate laws next class. Instead, we need to have some physical understanding of the number that really matters, which is K R. Right? What distinguishes two different reactions, right? In some sense, are these numbers right here, right? How many of each molecule is involved? That's important. That says me something chemical. And also the rate. So let's think a little bit. I think that's where we can get our physical insight, is to think about how do A and B contribute to the rate in their proportionalities, their stoichiometry, and why the number KR is what it is. We get a physical source for that. So our big focus today, in particular, is here. And we'll see once we analyze KR and understand what it means, that we'll start to understand why we have these stoichiometric powers here. All right, now I give you we're going to do all of this with a practical example. All right, I think the best way to think about kinetics, again, this is phenomenological. We're looking at real processes in the lab. So let's motivate this discussion with a real reaction. Right? So we'll go pull one out of really great example of a reaction. We'll pull it out of organic one. All right, we'll look at an example from organic chemistry. All right, I'll make a new page. Okay, so let's consider this reaction. We're going to take methyl bromide, and we're going to react it with some aqueous base. Right. It doesn't matter what base we choose. Well, it does, but in this time, we're just going to take hydroxyl radical. Right. And this is an equilibrium with methanol and bromide ion. Okay. Simple reaction. Anyone know what this is called? Does anyone remember workout what this kind of reaction is called? Ah, there you go. What does SN2 stand for? What can you span that word out? Yes. Bimolecular. Oh, so Angela's jumped like 10 steps ahead. So that's good. So this is let's keep on to that, right? So Angela says that this is a nucleophilic substitution reaction. And Angela aptly notes that we say that this is SN2. All right, now I'm going to put Angela under pressure. What's the mechanism for this reaction? Right, so let's look at the mechanism, right? So let's just do it like an organic chemist. Let's push electrons. Right, and we have SN2. How does that happen, Angela? Ah, fantastic. Fantastic, right? So we have methyl bromide. All right, I'm going to draw it in 3 dimensions. Right, the OH, as she says, as Angela says, comes in from the side or from the back. Right? And we get some sort of intermediate structure where the C pyramidalizes. Basically, these hydrogens are driven away, so planar form. You have a half bond with the OH. Sorry, let me draw that more properly. And a half bond with the bromine. That bromine leaves. Right, so we get, this goes here, and this kicks out. And we're left with CH3OH plus Br minus. Okay. Angela, do you know what the name of this intermediate's called? Do you know the actual name of it? Do you know who invented this? Okay. This is what's called the Walden inversion. Right. The cool thing is again, SN2, the way that you know that this happens is that if this is chiral, you have a right-handed molecule. When you do a substitution, that's SN2, it becomes left-handed, which means that the nucleophile has to come in from behind. It swaps the hand. All right, and she said that again, the 2 means bimolecular, right? So we can write a rate law for this. We could say that the time derivative of the concentration or the rate of formation of methanol is equal to some rate times what, Angela? What concentrations is this dependent on? Speak up, I'm sorry. Yep. And OH, right. Right, so it depends on both. Okay. Do you guys do this? Did you ever do this experiment, this kinetics experiment in Orgo Lab? You've ever done Orgo Lab? You guys measure the kinetics of this stuff? Really classic. And it's dependent on both. So, okay. There's an alternate mechanism for this. I have some space at the bottom. I don't. Right. And Angela's off the hook now. I'll finish this conversation. There's an alternate mechanism, which of course is SN1. It's called SN1, which is CH3Br. And what happens in this situation, let me actually draw this more properly. It gets a little easier to see all the bonds. Is that the alkyl halide ionizes first, and we're left instead of an intermediate CH3 plus Br minus, this ion, what we call an ion contact pair, right? We ionize the bond, and then OH flies in, right? And you get an ion exchange, which is extremely fast, and you're left with CH3OH plus Br minus. Okay, and this reaction has different kinetics. It has some rate, but it's only dependent on the concentration of the alkyl halide. What happens is that SN1 is a two-step reaction. You have one step, the slow step, which is the ionization, polarization of that bond to plus and minus, and then the OH comes in very quickly and substitutes that, negates that positive charge. So the OH doesn't have any dependence on the kinetics, right? As long as there's OH in there, basically the step of these combining is extremely fast. It doesn't matter. That's something to think about a little bit. Right now we have a reaction that has two steps, but the second step doesn't show up at all in the kinetics. Interesting observation. So the question, of course, is that, well, the way that I've drawn it, maybe it makes sense why they have different rates, different concentration dependencies, because I've drawn it such that the intermediate only depends on the methyl bromide, S1. Whereas the intermediate that I've driven here, the Walden inversion intermediate, involves both species, right? Bromine's in there as well. So that should make some sense that we see bimolecular dependence in the rate because they're both involved, right? But that's just, I'm just hand waving, right? Just hand waving this. You need to have some better physical intuition of why this is. Why is it that these are appreciably different? And it goes deeper than just that bromine is here and it's not over there. Okay? I mean, it has something to do with it. It gives us some hint of what's going on chemically. There's actually a deeper reason why the OH doesn't show up in the ester plot. All right, so what I want to do is I want to think about this reaction from a physical perspective, right? What is really happening? And remember that we have a tool in our tool chest, which is Gibbs free energy. We know that if we have some magical box, we can take any point along this reaction, any point we want, and calculate the energy of it. Not too hard. So we have some tools that we can track this reaction with energy. And so let's see if we can come up with a very simple model to understand how the energy changes as this reaction proceeds. Right? So let's think a little bit about what happens here, right? The key point, right? The key motion, if you will, in mechanism is bond breaking and bond formation, right? We got to break a CBr bond. Sorry, I didn't want this, right? CBr. To break a CBr bond in bond formation, right? Because we have to form a CO bond. Right, so let's think about these two processes separately. Right, let's think about the energy that the system has to expend, how the energy varies as we stretch that bond and we start to break it. Right, so I'm going to actually give you an equation that we're not going to really study too deeply until next semester, but there's a really nice model that we can write down for how the energy varies for a bond as we stretch it. In general, covalent bonds are approximately described with a potential energy function named after the white guy who came up with it, the Morse potential. And the Morse potential is a really simple function. We don't have to worry too much about what the function looks like. I'm going to write the formula down for it. We just need to analyze it on a graph. I think visually it's much more clear. And we could say that the potential energy of the bond as a function of the distance between the two atoms is equal to some number d sub e times 1 minus e to the minus alpha times r minus r sub e, another number, all squared. Right? Kind of a funny looking formula, but it has a really beautiful plot. Kind of jam this. I'll plot this up here. I have a little bit of space on the right here. Not really. Okay. Yeah, I'll plot it up here. Let me give you a little plot. Let me actually change that. So this function goes negative. All right, so let's think about a little bit about what the behavior of this function is as r goes to 0, as the bond becomes 0, two atoms on top of each other versus r infinity. So r infinity, this becomes a large number, and you exponent, you have e to the minus large. E to the minus large number is 1 over a large number, which is 0. Right, so this all simplifies to d sub e. Sorry, if this goes to 1, I'm sorry, this goes to 1. So we have 1 minus 1, so this goes to 0 at large distance. Excuse me. From 0, and then at small r, less than re, this number blows up. This number blows up, so this blows up. So at r equals 0, it goes to infinity. And at r infinity, it goes to 0. Once you track this, what you find is that it actually crosses 0. So the function, let me write it here, r and e, it goes to infinity, and then it comes down below 0. And then as r goes to infinity, it rolls asymptotically towards 0, like this. Okay, so it's got this kind of negative little well here. All right, and what we find is that when you do this analysis, that the bottom of this well is at r sub e. Okay. And the distance between the bottom point, right, the most negative energy, and 0 is d sub e. Okay, so let's if you guys remember the Lennard-Jones potential from like months ago, so it has a very similar formula. This is an attractive potential for a bond. So what this means is that long distance, the atoms are so far apart they don't talk to each other, so the potential energy is 0. As they start to come together, the atoms attract each other, lowering the energy. Right? Potential energy is negative if attractive. Lowering, there's some magical equilibrium point where the bond is perfect and the energy is minimum. And then as you start to push the atoms together, they start to repel, the energy increases and continues to increase. So the bond, right, the molecule, when it's sitting by itself, floating around, nothing happening to it, it sits right at this energy. So this is the energy of, this is in some sense, you could write that this energy right here, with the right choice of units, could be delta H of formation of our molecule. Right, so this is the energy of the molecule at equilibrium, 200 Kelvin. You can just say roughly that that's where that sits, right? That's where it is. Maybe it's delta G. It doesn't really matter what units we use for the energy. We can use Gibbs, we can use enthalpy, we can use total energy. It doesn't matter. It just depends on if we're at temperature or constant pressure, right? But in general, we have this kind of intrinsic stability to a bond, and there's some magic point where the bond is most stable, equilibrium distance. Okay, so this is where that molecule is sitting. Okay, so let's think a little bit about how the energy of the system changes through an SN2 reaction using this idea, right? So in SN2, right, we actually have two things moving, right? Remember the intermediate for this system is bromine leaving. And OH coming in. Right, so we're kind of actually have a motion that requires us to think about two different bond lengths, like the CO bond and the CDR bond. But the nice thing is that as the process of this reaction, one is coming in, so R is decreasing, and the other one is increasing. Right, so what I can do is just kind of draw this with two plots that are opposite each other. Right, so let me see if I can, let me just sketch this out for a little bit, and then I think you'll understand what I mean. So I'm going to have two plots. Sorry, I got to do it from the other way. Two plots of energy. And I'm going to demarcate them in the middle. Right? And this is that intermediate point. All right. So, and on this right-hand axis is going to be the CO bond length. And on the left-hand side, it's going to be the CBR bond. Okay. So if I were to draw these, we have some potential for the CBR bond length. That looks like this. And the CO bond length also has an equivalent one. But it's more negative, and I'll explain why in a second, than the CBR length. Right? There's some energy difference here. Right? Because this is the formation enthalpy. This minimum here is the formation enthalpy of CH3Br plus OH minus. And this is the formation enthalpy of CH3OH plus Br minus. Right? Those are our two limits of our reaction, the beginning and the end. Right? And they're going to be negative. This one's negative because the overall reaction is exothermic. Right? This is a product favored reaction. OH wants to replace Br because Br is a better leaving group than OH, right? Remember the weaker conjugate base is always the one that's preferred. And of course, bromide is a weaker conjugate base than OH. So the OH attacks and the Br leaves. So that means that the products are a lower energy than the reactants, just by definition, because it's a product favored reaction. Right? So you could say that this energy difference between these 2 points is delta reaction of H at our conditions. Okay, so let's think a little bit about how this reaction proceeds as we start to react, right? So we start initially, before the OH comes in, right? We have 2 points that we're sitting on in this bond. So we start here. Right? And of course, the CO bond is extremely long, right? So we could say, for instance, that the CO bond starts here. Right? And of course, now what's happening is that they're tracking in opposite directions. As the system reacts, this bond starts to lengthen. And this bond starts to shorten. Right? And there's going to be some point, right, where it seems like the energy curves meet. Right? There's some point here, too, where the energies are the same. Here, the E of the CO is equal to E of the CBR bond, right? Some middle point. And then this goes on and finalizes the reaction, and we get finally some final 0.3. And of course, now the Br is long gone. The CBR is there. Okay. So let's think about, now we have to think about the total energy of the system. Okay, so what happens now is that this energy for the CBR bond is 0. We don't have to think about it. So at the beginning, the total energy of the system is just the energy at 1. And then as we start to break the bond, the energy rises and continues to rise until it hits the maximum. Right? And then the maximum is where the curvature of the CO bond starts to kick in and it starts to go negative. Right? So it increases, and then suddenly now the system is at this middle point and the energy decreases. And then we left to the products. Right? So the energy starts low, it rises, and then it falls to the final point. So I can instead write this in a simpler way. right? I could draw another graph that is much simpler. So it just thinks about these three important points, right? There's three important points in this curve. There's the start point, there's the end point, and then there's this maximum. And everything increases to that maximum and decreases afterwards. So what I could write instead is something that looks like this, right? I could write just for some generic coordinate, right? Which is some combination of the CO and the CBr bond. Our system is at some energy initially, right? This is CH3Br. This is delta G, we'll say, for instance. It can be delta H again, it doesn't matter. I'm just going to be arbitrary with these and a little sloppy. OH minus. And the energy will increase to some point. And then it decreases to the products. And this magical point at the top, right, is some intermediate, right? And we know what it looks like, right? It's a bond it's kind of like CBr is halfway broken and COH is halfway broken. Okay. Right. Makes sense how I've gone from this to this. Right. We have a special name for these graphs, right? We've lost some information by converting to this graph, right? We don't really have a sense of the curvatures here, right? How much the energy. I've lost some kind of geometric information about the system, but I've got three important energy points. Remember, in thermodynamics, in some sense, we don't really care what happens in the middle. But you can see it's important here because the energy has to rise before it falls again. If we looked at equilibrium, considered equilibrium, just equilibrium itself, we only look at this energy difference, right? This energy difference between these two. Is delta reaction of G. But when we start to think about the actual physical process, there's some intermediate point that's much higher in energy than the beginning or the final point. Right? What we're going to find today is that the energy of this point determines the kinetics. It's the only thing that matters. This point right here. The fact that the energy has to rise in order to fall again ultimately sets the rate of our reaction. Maybe that should make sense to you, but let me convince you that that's the case. Right? So we call these little graphs of energy, we call them reaction coordinates. Right? And they're just little graphs that we draw that give us some information about the mechanism of a process. And so I'm going to write start and end. And we'll plot delta G. Right? And the system will say starts at some energy 0. Right? And the energy will smoothly increase until it hits some maximum value. And then the energy will decrease at some final energy for the end point. Okay? And we define by definition that the energy difference between the start point and the end point is delta reaction of G, gives energy reaction. And we mark this special point at the top, the maximum. The energy of this point, we give a name called E sub A. Could be delta G of A, all right, but I'll just call it E sub A. And this is what's called the activation energy. Might call it E sub A. I may sometimes call it E double dagger. Anytime you see that, we have a special name for that. This means activation. Right? And sometimes I might call it delta G double dagger. It just depends on the energy I choose, the energy function that I choose. Right? So sometimes you see it with this little a, sometimes you see it with a dagger. Right? Anytime you see a double dagger or energy of sub a, that usually means activation energy. It's the energy of this point. And for our reaction, right, we have a special structure that is this intermediate state that we've defined, right? That's halfway reacting. And we always give these a special label, this special energy, this activation structure. We give it a double dagger. And when we call that a double dagger, when we write a double dagger, we call this a transition state. Okay, a transition state, right? What we're going to find is that there are a lot, and we'll look at SN1 again. We might not. Next class, we'll probably look at SN1 quickly. Actually, maybe I'll do it really quick, and then we'll do that the rest of the work. So, the transition state is an intermediate with special properties. Not all intermediates are transition states. Transition states are unique. Transition states satisfy three properties. Two of them are related to each other. Right? One is that the derivative of the energy with respect to the coordinate, let's call the coordinate x, the derivative of delta G with respect to x is 0 at TS, at the transition point, right? And also that the second derivative is less than 0 at the TS. What this means is that it's a maximum. It's an energy maximum. Right? And it, not only that, it has to be a special energy maximum for reactions. And so 3 is a little bit longer for reactions involving multiple coordinates. Right? Maybe that's bond angles, lengths, etc. Right? Then it must satisfy that it is that the energy is a minimum along all the other coordinates. For y not equal to x. So it's only a maximum along one coordinate. So what that means is that you have it's like a three-dimensional surface of energy. You have different coordinates and the energy changes depending on them. And it only along one of them is it a maximum. All right, I can show you a really nice picture of this. Right, so a point on a surface with one maximum and n-1 minima for n dimensions has a special name. It's called a saddle point. All right, let me draw a picture of a saddle point for you. Instead of drawing it, let me just draw a picture, saddle. Let me just grab a picture from Wikipedia for you. Ah, beautiful. This is a great picture. So this is a two-dimensional set, one-dimensional, three-dimensional surface. There's two coordinates. Right, so you could think about this as, if you think about this as this direction as x and this direction as y, right? And this is energy. Z-axis like this. Right, along Y, right? Along Y, it's a minimum. Right, min along Y. And then along X, it's a maximum. Right? Every transition state has this property. It's a really important limitation because when you want to go onto a computer and calculate your mechanism for your reaction, this gives you a constraint to what to look for. You find points in between your products and your reactants and your products, where the energy is at a saddle point. This is how we find transition states on the computer. We look for points in between our beginning and our end points and find that saddle point. So I've got 2 minutes left. Let me just draw one more picture for you to compare this to SN1. Right? And I want to show you why SN1 does not have a transition state. It's chemistry. Well, it does have a transition state, but it's not what you expect. So let's compare that to SN1. Right? SN1 has a reaction coordinate instead. Again, the energy difference we can say is relatively the same. We have some 0 point here. That's our starting materials. We have some final materials. And so what happens, remember we start with CH3Br here. The first step is that the CH3 and the Br break into 2 ions. So of course that the energy is going to increase. Right? And then eventually you have some ion pair. So there's some energy to break it, and then the ion pair stays. And so here at this point, you have CH3 plus and Br minus. And then the OH is going to come in later, right? And take that. That has no barrier. The energy decreases like this. Maybe it has a small barrier. Right? So you would say, okay, the way that I've drawn this is that this is the intermediate, right? It's the middle point of the step, right? It's after the first step and before the second step. But in fact, this is at a minimum. These are in substance stable molecules. They're not very stable, but they're stable species, right? In the sense that their energy is at a minimum. They are an energetic, they exist at a minimum in delta G. Now that delta G might be way higher than the products or the reactants, but it's at a minimum. So therefore it is not a transition state because the transition state is at a maximum. So what we call this is an intermediate. This is a chemical intermediate. Right? So it may be long lasting, it may not be, but it's some stable, long or short lasting chemical material, lasting molecule or molecules. They're at an energetic minimum. They're real molecules. Right? And so what is the transition state of this process? Well, the transition state is right here. Sorry, is there some energy hump that you have to break the bonds? Right? So the transition state is this step right here, right? And what is the transition state? Well, that's just the CH3 and the Br struggling to fall apart. Actually, it's not even a transition state. But you can kind of think of it as a transition state, some intermediate point where you have this CH3 with some positive charge and some Br minus with some negative charge. Right? You're still stretching it about. right? And likewise, right, if you think about this as the TS, like a pseudo transition state, right, it only involves CH3Br. Right? But in SN2, the TS involves both CH3Br and OH. They're both involved in the transition state, right? And therefore, the kinetics reflect those transition states. So therefore, the rate law is dependent on the concentrations and stoichiometry of the transition state. Right? That maximum point in energy you have to cross, whatever is involved at that point, maximum energy determines your kinetics. It's the hardest point to get over. So obviously, whatever makes it easier to get over that influences your kinetics the most. And so whatever structure you have at that transition state determines your kinetics. So in SN2, both of them are involved. So you have dependence on both of them. And it's 1-to-1, right? You have one OH and one CH2Br involving each other. And so the kinetics are first order in both. Whereas in SN1, only a CH3Br is involved because the transition state is the ionization step. And so therefore, it's only first order in the halide, and the OH does not involve itself at all, because once you have a CH3 plus, that OH will come in and react instantaneously. Pluses and minuses together has no barrier. Purely attractive. So there's no barrier on this side, and therefore the rate does not depend on it. It only depends on the ionization. Right? So that's why in SN2 reactions, the SN2 goes here. Why SN2 happens here, not SN1, because the transition state here requires you to stabilize a methyl cation. And methyl cations are not stable. They have very, very high energies. It's certainly possible to make one, but it's not very favorable. Whereas if this were a T-butyl group instead, see where instead of hydrogens, it's methyl groups, it's much more stable. The T-butyl cation is much more stable. So this transition state is lower. And compared to SN2's transition state, it is net lower. And so T-butyl bromide goes through SN1 because its TS for ionization is lower than it is for the 2 molecules step in SN2. Right? So both reactions happen. Both mechanisms happen all the time. It's about which one is preferred. Right? Which one is energetically preferred? And what we'll see next class is that the only thing that depends on is which one has a higher or lower transition state. That's ultimately what determines kinetics. Okay, so I ran out of time, but we'll continue that. Oh, wait. Oh, we have another 30 minutes. Oh, fantastic. All right. I'm sorry. I don't know why I thought it was. I don't know what I'm smoking today. Okay, I'm sorry. So let's take a stop for a sec. Okay, so transition states are the critical piece of information to determine kinetics. That's really, really nice. We only have to determine the energy of one point to understand everything, as we'll see. But the problem is that the transition state doesn't exist. It's not a stable point in the energy curve. So you can never isolate it. You can never observe it either. But you know that your system has to pass through that point. You know that it has to pass through. So the question is there a way we can measure it indirectly? Right? Is there a way we can measure that activation energy without having to be able, if we can't isolate it, right? We can't equilibrate to it. We can't measure an equilibrium constant for the transition state. It's impossible. We have to find some indirect way to do it. And thank God there is one. Sorry, I used the other class, which gives out 445. That's why I'm confused. Okay, so let's go back. Now let's just do a little bit of thermodynamics. Very, very simple thermodynamics. We don't have to do much to get an answer to this question. So let me just draw one more reaction coordinate. Okay. So I'm not going to do delta G. I'm just going to call this E. All right. This is some intrinsic energy of the molecule. Imagine we're just looking at a reaction of molecules at 0 Kelvin. Of course, that doesn't actually work. But imagine you can track this. It's just the intrinsic energy of the molecules. No entropy, no heat, nothing like that. Okay. So this is the intrinsic potential energy surface for the molecules, just a function of the bonds and their relative energies. All right. So what we're going to do now is we're going to put this system in a bath at some temperature. Right. And let's think about this classically. All right. So here's EA. Oh, sorry. I knew I hit something. I know how to fix this. There we go. Okay. Right. So imagine we start with some molecules here, right, from CH3Br molecules. Think about them as balls, right? And so what the reaction is doing is they're rolling the balls up the hill. You start here, you roll the ball up the hill, some random amount of energy specified by your temperature. And if you roll the ball hard enough and you get over the hill, it comes back over, right? So the kind of criteria we have for this reaction to happen is, in some sense, how many balls that we roll at some random energy gets over that barrier. Okay, so randomly our molecules are given some energy via heat, and any molecule that has energy less than E sub A doesn't react. Right, so I can shade that area, right? We have some series of molecules here. Well, actually, let's do it like this. Let's start over. You can get the idea, right? We want to think about how many molecules have enough energy, right? So our goal here is that at a given temperature, calculate percent or fraction of molecules where their energy is greater than or equal to E sub A. Right? That's our goal. Okay, so we have a nice equation for that at equilibrium. We can calculate the fraction of molecules at any energy using Boltzmann's equation. We can calculate the number of molecules at energy E sub A, or let's say energy E, over the number of molecules at energy equals 0, is equal to E to the minus E minus energy 0 over RT, right? Our Boltzmann equation. Right? And we'll set E0, right? By definition, this is E0. We'll set it equal to 0. So that says that the fraction of molecules at energy E is just equal to E to the minus E over RT. Okay. So what we want to calculate now is, in some sense, right, we have some fraction of molecules that don't have enough energy. Right? These are E less than EA. Right? And then there's some fraction of molecules, we don't know how much, that have a sufficient amount of energy. Right? These are molecules of E greater than or equal to E sub A. Right? So how do we calculate that? Well, the number at any given energy of molecules at N sub E, fraction compared to 0, N sub 0, is just E to that minus energy. Right? So what we're going to do is we're going to step our energy from E sub A to infinity and ask how many molecules do we have at each energy. Right? So we're going to ask at E sub A how many molecules are at that energy. how many are E sub A plus 1, E sub A plus 2, E sub A plus 3, all the way up to infinity. Right? And of course, all that is just an integration. Right? We're going to integrate over the probability, the distribution from our critical energy out to infinity. Right? In some sense, all we're doing is we're calculating the probability or the fraction of molecules that have enough energy. Just an integral. So the number of molecules with E greater than or equal to E sub A divided by N naught is equal to the integral from E sub A to infinity of E to the minus E over RT dE. Right, just integrate over all those energies. That's a really easy integral to do. Integral of an exponent is an exponent. And so we're left with 1 over RT E to the minus E sub A over RT. Okay, so the number of molecules proportional to E sub A or greater is just proportional to E to that energy divided by RT. All right, so this gives us the fraction of molecules that are reactive at some point. Right, when the reaction starts, this is how many molecules are ready to go. Right, so we can calculate then, right? We want to now calculate the rate at which this happens. Okay, so what we can do now is then calculate the rate, right, which is the number of reactions per second. That's going to be equal to the probability, or rather, I should say the proportion. Let me say the number of the number of greater with enough energy times the number of chances to react per second. All right. So every time the reaction is ready to go, however many times per second that is, that's a tough question to answer. You can imagine that there's some process that's happened randomly. Everything has to get in the right orientation to happen. So that happens some number of seconds, right? The idea is that the OH and the CH3Br are moving around together in every fraction of a second. Some OH aligns perfectly with the CH3Br, ready to react, right? So there's some number of those chances, those opportunities for reaction. And then, of course, when that opportunity happens, the molecule has to have enough energy to react. So the number with the right energy times the number of chances gives us the total rate. So what we write then is that the rate constant, Kr, which has units of inverse seconds, right? That's our rate constant, right? Which tells us how fast the system reacts per unit mole, is equal to some number A over RT. So this is equal, A is equal to some number over RT, where is the collision frequency or the reaction frequency. Okay, so that's how many opportunities you get per second. We'll see that this is related to collisions. Collision frequency. Right? How many times does an OH collide with a CH3Br? Times E to the minus EA over RT. Right? So the rate constant is just a function of two things. Some speed of the reaction, some chances that you get, of course, is dependent on concentration, probably, temperature. Obviously, it's dependent on temperature. There's a T in it. And it's also dependent on the activation energy. Right? That's the most important number, activation energy, right? Because it's E to that. So as the activation energy changes, the rate changes exponentially. Right? So this is called the Arrhenius equation. All right. And it gives us a way to measure activation energies through experiments. All right, let me show you, let me prove to you that that's the case. All right, recall that we can measure the formation of methanol with respect to time is equal to Kr times the concentrations of your reactants. Okay, these are all things that we can measure in lab. Right, so we've got these in lab. And this is something we can measure in lab as well. Okay. Right. And so what we want to do is determine Kr. Right? So we can get a value of Kr from experiment, right? We get this from, this just comes from our results. Right. And then we can get it at different temperatures, right? We can do this at different temperatures. We did the same reaction over and over again, measure Kr at different temperatures. All right, now what we can do now is we have all these Krs, we have all these Ts, right? So we have some data set that looks like temperature and Kr, right? Maybe it's at 298, it's 1, 373, it's 4. I don't know. Anyway, blah, blah, blah. Some data set. Okay. And what we can do now is apply Arrhenius by taking the log of both sides. We're going to apply log. So that says that the log of Kr is equal to the log of A e to the minus EA over RT. All right, we got some simplifications we can do here. This says that the log of Kr is equal to the log of minus EA over RT, e to the minus EA over RT, plus the log of A. And log of E is 1. You can bring out the exponent. So we're left with minus EA over R times 1 over T plus log of A is equal to the log of the rate constant. All right, why is this important? Well, if we call this Y and this thing here M and define our X variable to be 1 over T and log of A to be our intercept, we have a line. This is a linear function. All right, we have Y equals mx plus b. Do I have any room left on this board? No, I'll go to the next board. Right. So I can now what I can do is I can take my data. Let's do it like this instead. No, let's not do that. Sorry, I wanted to have the right orientation for these. There we go. So I could take the right, I can take 1 over T for all my data and plot as a function relative to it the log of the Kr that I'm measuring each of those temperatures. Maybe I have a couple temperatures here. Right, and what I find is that these correspond to some rate. Right, different rates. And what I get is a beautiful straight line between the curve, the data, like this. And the intercept is log of A, right? It tells you the collision frequency. And the slope of this line is equal to minus EA over R. Okay, so by measuring KR versus T, we can determine the activation energy directly. This is how we pull out that kinetic information. So log of A, right? You can kind of think of log of A as being kind of what is this? This is small 1 over T. And so this is the rate at infinite temperature. All right, so log of A, right? You can kind of think, right? Log of A is the rate at T goes to infinity. So A is equal to the rate as T goes to infinity. All right, so it's the high temperature limit of reaction. Right, and what does that mean? Well, that just means that EA in this limit is much smaller than RT. Right, so basically has no activation energy, right? So this is the rate independent of activation. Right, so that kind of gives you a sense, right, that that's kind of the maximum possible rate that it can occur at, right? This is the idea that every time something hits, CH3Br and OH hit, that they react, 100% probability, right? So this is kind of the high temperature limit of the reaction. Let me clean this up. Temperature. Right, and do I want to say anything else about this? No, that's about it. Right, so this is the maximum possible rate at given conditions with no barrier. Right. So it turns out that in general, this limit is ultimately limited by a number. And so typically A in most situations is around 10 to the 12 per second. It's around 10 to the 12. There's a lot of reasons why that is. I'm not quite ready to explore them yet, but 10 to the 12 is kind of a good approximate number. Sometimes they're less, sometimes they're more. Usually around 10 to the 12 per second. Right, so that means that roughly a reaction takes about a picosecond. To the time scale of the reaction, the time of reaction is around 1 picosecond. And most reactions tend to be on the order of a couple femtoseconds to a couple picoseconds. Typically. Of course, it depends on the temperature, your density. If you're in like a gas, for instance, and you have no collisions because everything's so far apart, A is tiny. There are other reactions where it's inversely proportional as well. We'll look at those. So A is kind of a complicated number. But the important thing is that phenomenologically, these are numbers that even though we can't measure them directly, in the sense that we can pull out the activation complex and say, hey, what's your energy? We can measure them indirectly through phenomenological methods, through empiricism, and through measuring things in experiment. Right? So most kineticists in the world are experimentalists because that's the way we do things. Measure kinetics, experiment, and we create models to explain those kinetics here. Coming from bottom up by taking two molecules and thinking about how they react, and then taking that knowledge and expanding it to a mole, right? Starting microscopic and working macroscopic is much harder to do than the other way around. Because macroscopically, we have all of these tools that give us all the values we need very, very easily. Right? This is the easy experiment in the world. If you can measure how much product you're making per second, and you can change your temperature in your hot bath, you can calculate the activation. That easy. But doing it the other way around, by taking two molecules and thinking, hey, how do I move these around? How does the energy change? It's not like a little box of two molecules, and how the energy changed, what's the transition state energy? What's that structure look like? And then how does that extrapolate to macroscopic environments? And how do I get this information out, say from a calculation? That's much harder to do. Because you have to understand very, very sensitive functions of how those two molecules interact with each other. You have to understand how that OH comes into the CH3OH. Doesn't come in any specific way, in any sort of random way. It comes in a specific way. As Angela said, it comes in from beyond. Right? And so you imagine you have some generic reaction you don't understand. So coming up with a way to understand how those two things combine is very, very difficult. And then to take that and extrapolate kinetics, that's very hard. But the other way around is much easier. All right, so what we're going to do, I'll stop here, but let me just finish one more statement, right? So we have this idea that activation energies determine our rate. We also have the knowledge that the concentration dependence in the rate law, how do each of the molecules that are reacting involve themselves in the rate law, depends on how they appear in the transition state, right? In SN1, OH is not there because OH isn't in the transition state. So we have that knowledge that the activation energy and the activation barrier have some knowledge that allows us to define it's correlated directly with the rate law. So what we're going to do now is look at rate laws, right? So what we'll come back to now that we have an understanding of what KR is specifically, we can now look at different types of reactions and see if we can use this activation energy argument to start to understand how different reactions and different rate laws form and how they evolve in time. Okay? So we'll start looking at that on Wednesday. Once we're done with next class, you'll be able to tackle the whole homework. Right? Just one more lecture. Have a good one, guys.
Yeah. What about Jack? This is weird.
Like amino acids, because I think that they were on just those selections.
Oh, they were. Yeah, they were.